All right. So let's get started. Hello, welcome. So today in section what I'm going to be primarily talking about is Design Project 2. All of you, I hope, have seen it by now and started working on it. There have been some new postings to the web that you guys should all look at. Most notably, automated test bench processing, basically the same test benches the same sorts of test benches that were used in Project 1 have been posted to the website, so you can start using it for performance verification. So I'm going to really briefly go over the project handout, and then there's also an additional handout that clarifies some things that I'm going to go over as well, and then start talking about general design strategies. So, can we zoom in tight on this sheet here? Great. Great. Okay, so so everyone knows what the project is, and just to go down the design specifications and clarify things. So L-min, W-min, same as before. A difference on this project is that there are now two VDDs over which your circuit needs to operate. And the test bench processing will do that. So it's basically VDD is 1.3 plus or minus 0.1 volts. So 1.2 and 1.4 volts are the supply voltages that we test over. And that's the reason we're doing this is twofold. One is because in actuality, when you're out there designing circuits, supply voltages will actually vary. You can't guarantee an exact voltage for a whole host of reasons. So you want your circuit to be robust over a range of supplies. Okay, so that's one thing. And the other thing is that, and I think I mentioned this last week in section, is that a lot of times in class or on your design project 1, people generated bias circuits by doing things like this. Oh, thanks. So generating your master bias by putting a couple of diodes back to back or something like that. And you did that because that's the lowest area kind of circuit you can do. Now, in reality, this is a very area efficient circuit, but it's not a very supply robust biasing circuit. As supply goes up and down, that extra supply shift needs to be dropped over the VGSs of these two devices. So therefore, the VGS increases, so the current increases. This is very supply sensitive. So you probably want to come up with some circuits that are less supply sensitive. Otherwise, your GMs and your VD-SATs will vary quite significantly, and hence your gains and all that other stuff will vary quite significantly as you vary supply, and might sort of push you out of the operating region that you want to be in. Okay, so the load resistance here is 1 kilo ohm as before, and again, don't include that. RS, which is something a little different, something new. Now there's a source resistance on each driving side, and those are each 500 ohms. And the reason for that is because we want there to be a pole at the input. Chances are your input structure will look like either an NMOS or a PMOS diff pair, and if these are driven by ideal voltage sources, it doesn't matter like what capacitance this is, right? So any capacitance wouldn't create a pole, but in reality, and no driving circuit has zero impedance. There will be some finite source impedance, and so as a result, you'll have Miller effect, and you'll have a pole at this node. Okay. So, getting back to this, so that's RS. You have a spec for the low frequency voltage gain, which is basically the DC voltage gain. And you also have a spec for the common mode voltage gain. Now the common mode voltage gain, and I'll talk about this a little later, is actually not just the low frequency common mode voltage gain, it's the high frequency common mode voltage gain as well. So this is wrong here. This should say high frequency. It's high and low frequency. And I'll talk about, and we can sort of start analyzing some circuits that where the common mode, oops, it should be here, high frequency, where the common mode gain is a function of frequency. Just like the differential mode gain is a function of frequency, there's no reason why the common mode gain wouldn't be a function of frequency as well. All right, the input common mode is basically what you specify, and it's going to go up and down plus or minus 150 millivolts. The output swing is as before, and now instead of having an FOM that is a product of your area and your power consumption, we're setting the supply current to be equal to the maximum current you're allowed to dissipate to be equal to 1 milliamp. And there's other stuff. There's something that I want to get into on this as well that I'll talk about in just a second. And what you're looking to maximize is the 3 dB bandwidth of the differential mode gain. Okay? And it says here he specifies that ACM as a function of frequency must remain less than 0.1 over the bandwidth. So from DC to the 3 dB frequency, which is calculated in our test script, the maximum value of ACM, or the absolute value of ACM, must be less than 0.1. Okay? So then on the back, more of the same, and how it's graded, but that's all stuff that you know. Okay, so a big important announcement. I guess, can we zoom out? Don't zoom out so much. So this is the new handout. And the big important announcement is that there are a couple of new handouts on the web page. One is this, and the other are all the test benches. And now there are 3 test benches. So the report guidelines, and Professor Broderson spoke about this. So focus more of your analysis and your report on maximizing the 3 dB frequency. You don't need to spend so much time on all the DC solutions and stuff like that. Okay, and then this note. So let me explain how we calculate power consumption, or current consumption. So let's assume, and we can, well, don't zoom out too much, because I'll be zooming back in just a second. So this is your amplifier. Okay. So this is basically what your amplifier looks like, right? And so this is I1, and let's call this I2. Okay? So what is the power dissipation of this circuit? The total power dissipation in this network. Power dissipation is equal to the sum of Vx times Ix, where V is the voltage across a certain branch, and I is the current across a certain branch. So the voltage across this supply is I1 times VDD, okay? And the voltage across this supply is I2 times VDD over 2, okay? So the net current consumption can sort of be defined as I net is equal to the power over the supply voltage, okay? So if you do that, you get is equal to I1 plus I2 over 2, okay? Everyone see that? So this is actually how we define the current consumption that needs to be kept within under 1 milliamp. This must be less than 1 milliamp. And this has to be less than 1 milliamp, I believe, under the entire range of VDD and Vout. Okay? So let's assume that your output stage has an NMOS and a PMOS device. Okay. So let's call this IP, this IN, and this iLoad. Okay? So this was formerly called I1, and this was formerly called I2, but I've changed it now. So this is equal to IP plus IL over 2. Okay? We know that by, and I intentionally didn't draw what's driving these gates, because I don't know how you chose to implement this. I don't know if you chose to implement this as a common source NMOS with a PMOS current source load, a common source PMOS with an NMOS current source load, whether or not you did something funky like a totem pole driver, and that's something that we were talking about in office hours today that I'll touch on briefly. But so whatever. So we know, so iNet is equal to that, and we also know that iLoad is equal to IN minus IP over 2. Okay? So therefore, iNet, you substitute this into here, and you get IP over 2 minus IN over 2. Okay? If this were the only portion of your amplifier. In addition, you've probably got some, diff to single over here that's sourcing, some I3 or I0. Okay? But the net current consumption of, is that what you wanted? This should say plus, but it is over 2. Because IL, if the current consumption, if IN and IP are exactly equal, and therefore IL is 0, what's the net current consumption? The net current consumption is IP or IN, right? So if we were to say IP plus IN, that would be 2 IP, which is wrong. It's off by a factor of 2. So this is the correct answer.
No, I just don't like IL is IN minus IP by 2.
Oh. That's totally correct. Okay, I made a math error there. I'm sorry. You're absolutely right. This statement's correct. IL is IN minus IP. Thank you for catching that. Okay. So that's how we calculate device current. Or that's how we calculate current consumption. And so the thing to note is that, okay, so depending on how you implement this, one corner or the other might have, in other words, Vout equals, so Vout is going to equal either 0.3, 0.6, or 0.9, okay? One corner or the other of these, depending on your implementation, will probably have the highest net device current. For instance, if the PMOS is a current source, and this is your common source transistor, so it looks something like this. And so this is I bias, call it whatever you want it to be. The highest current consumption, you know what, I'll draw it on a new page. People keep telling me that I write too small. So if this is your output stage, then the highest current consumption, I max, is at Vout equals 0.3 volts, because then we've got 300 microamps flowing in there, right? So IN is equal to IB plus 300 microamps. So I net is IB plus IN over 2, so it's equal to IB plus 150 microamps, okay? When V out equals 300 millivolts. However, if you do it the flip side, if you have a PMOS output stage, okay, then Imax is when V out equals 900 millivolts, because now you've got current flowing this way, and that means more current flows through this device. And so in that case, I net V out equals 900 millivolts is equal to, again, IB plus 150 microamps. Does that make sense to everybody? So you just need to make sure that when you analyze for the maximum current, that you're analyzing the right corner. Okay? And from a device current consumption standpoint, now you don't need to minimize current, but you also don't want to be too wasteful with it, because if you're too wasteful with it, then what happens is that you can't use it in other portions of your circuit to maximize the 3 dB frequency. Okay? So, for instance, a good circuit that conceivably can be used to keep the current consumption lower is the totem pole, which the very simplistic totem pole, the simplest totem pole, and this is a bad totem pole to use, so don't use this, is the good old digital CMOS inverter. Okay? This has gain. This has negative gain. But the reason why this is a bad amplifier to use is that, so at VM, so when V out and V in equals VM, then this guy is sourcing a ton of current, and this guy is sourcing a ton of current, and no current goes out. The case where no current is delivered to your load, both these devices are sourcing a lot of current. But instead of what you can do is have some kind of level shift between these devices, and that can be implemented by either driving here or, as an alternative, driving the NMOS node. It doesn't really matter. Then you can set this up such that at the quiescent point, IQ is relatively small. Both these guys are barely in strong inversion in the saturation mode. But then as this node goes up, this guy pulls more current. This node goes up. This device basically turns off. And so it ends up, as the node voltage goes up, it ends up mostly looking like this kind of device. Vin goes up. And as Vin goes down, the exact opposite happens. This guy sources more current. This guy basically turns off because you're dropping the gate voltage, and it ends up looking kind of like that. So in some sense, it's a push-pull, but it's pushing and pulling from opposite directions, so to speak. Yeah?
So I thought about this circuit, but how do you bias it independent of the supply?
Yes. Perfectly, very intelligent question, and something that can be a real problem. So let's start talking about how do we create this battery voltage. That's the general question you're asking, right? Okay, how do we create that battery voltage? Well, you don't have batteries at your disposal. So ways to do it. So let's say we've got So this is our device, and we want some battery. And let's just assume for the sake of argument that we're driving it from the PMOS. No reason why that's the case, but I'm just doing that. It could be from the NMOS. So what you can do is you want to create a battery. So the question is, this is what I was talking about in section. How do you set up the biasing of this battery voltage in such a way to get the devices where you want to operate and to do it independent of voltage supply? So this is sourcing some current IX. IX, okay? So that being the case, and let's call this VN and VP, okay? We see that IX has to flow through here, and then it just gets sucked out by this, okay, to balance KCL. Now this IX that's on this node could be part of whatever the driving amplifier is. Like, you don't need to explicitly put that here, but doing it just helps keep things balanced. Okay, so that means that, and this is R, Vn is equal to Vp minus Ix times R. Okay, so you have a fixed battery voltage here, right, effectively. Now, this could also be, you could also do it with an NMOS diode or a PMOS diode. You could do it with a diode-connected transistor across this guy. Okay. Now, the issue is, well, so let's assume that this amplifier, so the driving amplifier, and I'll draw it over here, was an NMOS input PMOS load diff pair, diff to single-ended converter, and this node drove right there, okay? So this is, let's call this 2ID. So this is ID, and this is ID. And so this device is ID, as is this. And we know that with zero differential drive, these two nodes are equal in voltage. So if this has a W over L1, if we put W over L1 on this voltage, on this size this guy exactly equal to this guy, we know that categorically we'll be sourcing ID here, right? That's kind of that's what I went over for design project 1, a way to just set up biasing appropriately. Now, so this voltage will be some VGS down from the supply to get that exact voltage. So to get that exact current. So VP is going to be equal to VDD minus some VGS 1 that's just sized exactly correctly. So that means that VN here, VN is going to be equal to VDD minus VGS1 minus IX times R, right? So as VDD goes up, this is going to stay the same. And if IX is constant over supply, that means as VDD goes up means VN goes up. And as VN goes up, the I that this IN will also go up, right? And it'll go up as a strong function. And that's the exact question that you're asking, right? So the question is, and the question is, how do we get around that? How do we solve that? Okay. So, does anyone have any suggestions? I talked about this in section. If we do a scheme like this.
You mean your office hours?
Yeah, office hours. What can we do? This is the expression for Vn, right? And we want Vn to stay to basically be independent of supply, right? How can we do that? VDD goes up. Is VGS? Do we have any control of VGS1 as a function of VDD? No, we don't. Assuming that ID is independent, the VGS on this device to source ID in the PMOS device is going to be fixed. Can we change R? as a function of VDD? No. I mean, a resistor is a resistor. IX. IX you're creating. And IX is going to be slaved off some master bias, right? So if you make IX VD have some dependence, IX is a function of VDD, then perhaps you can get this exactly right. So you want IX to be some constant value. If we want, okay, well let's call this VBAT. We want VBAT to be equal to some V0 plus VDD. Okay? And there are some questions as well. Wait a second. Do you want it to be exactly VDD or just delta VDD? And the point is that depending on how you define what V0 is, you can make it exactly VDD. And what I mean is that for each millivolt that VDD goes up, you want IBAT to go up 1 millivolt, VBAT to go up 1 millivolt. Okay? So, you know, how can you generate a current that is roughly proportional to VDD? There are lots of different ways. And one way that might work the simplest way, there's certainly more accurate ways. So if you make W over L big, and what is I out? I out is equal to VDD minus VT over R, right? So therefore, I out is equal to some I fix, which in this case is VT over R, plus VDD over R. Okay? So therefore, if you plug this into, if you plug this current I out into IX, you'll get some fixed current plus some current that's directly proportional to VDD, which will basically, so if you size this R and this R exactly the same, or do some ratiometric design, you can get this to be directly proportional, IX to be directly proportional to VDD, and hence this battery voltage to be directly proportional to VDD.
So is that I fix?
Yeah, and I fix is equal to, I'm just calling it I fix, basically some current that is independent of supply. And in this case, the fixed component is a negative current. It's minus VT over R. Now, in reality, you'll never actually get a negative current because a condition for this to work is that VDD is greater than VT, right? So this doesn't work exactly because, remember, there is some VDSAT on this device that is current dependent. But if you make this device big enough, you can kind of get rid of that, and the residual stuff might not be so bad. Okay? So that's one thing. And the other thing to keep in mind is that let's assume that, so the two voltages you have to design around are VDD equals 1.2 and VDD equals 1.4. Okay? Now let's assume that you design it such that at 1.2, and these currents are fixed, so you're not doing this hack or this tweak that I'm talking about over here. These currents are fixed. Let's assume that at VDD equals 1.2, you get it such that the NMOS device current is exactly spot on. It's exactly equal to ID. Okay? Therefore, at 1.4, this device current is going to be way off, right? So that's one design strategy. Fix it at 1.2, and then it'll be way off at 1.4. A second design strategy is make it such that at VDD equals 1.4, this current is exactly correct, in which case you'll be way off at 1.2. Now, the obvious sort of middle ground is to design it such that it's spot on at 1.3 volt supply. Therefore, as you deviate from that, so it'll be correct, the exact output voltage will be correct neither at 1.2 or 1.4, but the error will be bounded. You'll be balancing your error. Okay? So I want to pause on this stuff for a second to make sure that it's all sunk in and answer any questions about it. Yeah?
Can you explain that again?
Define that.
That stuff.
This whole thing, or the strategy about balanced design at 1.3? This. Okay. How about we talk for well, how many people want to see it again? How many people are so confused? All right. So let's just spend 5-10 minutes at the end of section after I let everyone else go, going over this, and we'll do it in a smaller group so that we can make sure everyone gets everything. Okay. So that's the output stage. What else do I want to talk about? Give me 1 second. All right, so going back to this handout, can we zoom in tight again? Thank you. So this note is what I just went through. Circuit submission guidelines are exactly the same. Now, people were asking, hey, there isn't a CGS or a CGD parameter in our device model. What gives? That's actually not true. There is, but it's just kind of implicit. So I wanted to go over really briefly how you calculate the device models, okay, or the device, the area drain, area source, and the various device parasitics, okay, when it's not implicitly given. And basically the model that we use is level 2 ACM is basically how the capacitor model is derived, and then a geometry parameter. So HDIF is a parameter that's given in your device model, and that's basically the distance from the contact. This is HDIF. It shows it right here. Okay? So therefore, and you can sort of see this is a source, this is a drain, this is the gate, this is W. So the area source, area drain is equal to 2 times HDIF plus W, because this distance is 2 HDIF times W. So that's the area of the drain. The perimeter of source and perimeter of drain is 2 HDIF plus W plus 2 HDIF, so it's 4 HDIF plus W. Okay. And so in order to calculate CDB sidewall and CSB sidewall, you need to calculate the perimeter of the drain and multiply by CG, the junction cap, the sidewall junction cap. Okay? And you also, there's also a portion here that if you look underneath, so I'll draw what the device looks like. So source, drain, gate, bulk. This portion here, there is a thin channel up at the top for conduction, but this portion here also has a cap. And so that's called the gate sidewall, gate side sidewall capacitance. And that's just basically this parameter CJ gate, which is given, times W. Okay, so that's how you get the source and drain capacitance. Okay? The source bulk and drain bulk capacitance. The other question is, how do you get CGS? Well, that's just 2/3 WL Cox, right? CGS equals 2/3 WL Cox in saturation. And then CGD0. Okay? CGD0 is, let me draw again this device model, gate, source, drain. So what is the actual physical mechanism that causes gate to drain capacitance? It's the fact that the gate and the drain overlap. So you've got some parallel plate capacitor here. Okay? And the parallel plate capacitor, so this is in 3D. So this distance here, I believe, is called LD. This dimension here is called W. So the area overlap is equal to LD Is it LD or LDIF? LD times W, okay? And Cox is equal to Eox times over Tox, which is capacitance per area. So therefore, capacitance CGD is also equal to CGS overlap is equal to LD times W times Eox over Tox. Okay. Oops, sorry. So that's actually in the model, although it's not explicit. Yeah.
I'm just kind of curious, in an analog process, do they do anything, since that Miller capacitance is devastating, do they make any effort to shift that overlap away from the drain?
There's no such thing as an analog process when it comes to CMOS because everybody, 90% of CMOS is digital. So the reason why you can use analog and it's so cheap is because you're piggybacking on a digital process. And this does affect the digital guys as well. And it comes down, and there really isn't anything you can do about it because it comes down to whatchamacallit. It comes down to the way the devices are fabricated. And so basically they use a self-alignment procedure that ideally, so they put the gate down first, and then they bombard the silicon with implant to create like an N plus and an N plus region. And then after they bombard it, so now this is perfectly aligned because they're bombarding on a straight angle and all the other N plus, so they bombard, 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 bombard. And then what they do is they do usually a heat annealing, and that creates a lateral, these particles diffuse. So there's a lateral diffusion, and there's nothing you can do about it because after you bombard with an implant, you've sort of messed up the crystal structure of silicon. So you need to heat it to enable it to sort of re-anneal and to re-anneal. So there's nothing you can do about that overlap. Good question, though. All right, and so finally,
Why don't they make up for the lateral diffusion by bombarding a little bit away?
because they can't, because they're actually they're not using a separate mask. They're actually using the gate as a shield. And you need to make sure, the other problem would be, so you're suggesting push it further away. So what would actually happen is so let's say you did this, that's what you're suggesting, and then you anneal to get it to align exactly. You can't guarantee that it's going to align exactly. Let's say it anneals and it anneals to this, so you've got some distance here. This gate can invert the channel here, but it might not be able to invert the channel here because it's not directly over it. So therefore, you wouldn't have a conductive channel from source to drain and your device would fail. So this is actually something, it's a parasitic effect, but it's a parasitic effect of doing something that's pretty much necessary.
So the lateral diffusion is kind of random.
It's well controlled, but it's not perfect. I mean, none of these things are perfect. And that's sort of part of what I was talking about before. You're not going to get exactly the same VT from process to process. They're cooking things. It's like, you make brownies in the oven. Sometimes they come out a little soft. Sometimes they come out a little hard. Sometimes there's too much chocolate. You try to do as best as you can, but if you're not ridiculously precise, you can't guarantee things to infinite precision. Anyways, moving back to this. One other thing, and this hasn't been implemented in the device model yet, I don't believe, but will be soon, is that a lot of times you want to connect, in an NMOS or a PMOS for that matter, the source to bulk. You want to do that? Actually, I'm going to draw it for a PMOS, just because I want to. Okay. So what that does is that turns off the back body transconductance, and it also lowers the VT. All good things. In the previous project, what we said is that it doubles the area of your device. It actually does more than that, but that's just a simple way to calculate it. And the reason why it actually doubles it is that now, so in a PMOS device, you've got a P plus region P plus region, you've got an N well here, and then P substrate here. Okay. The reason why is that you can no longer, if you connect, so this is the source, if you do a little connection here to here, you can't connect this bulk, this N well to the N wells of any other devices. So you need to sort of isolate it. Becomes a bigger device. An additional thing that happens is that this P substrate is grounded. So this is grounded, and this is some higher voltage. This voltage is greater than 0. So now you've got a reverse bias diode here, which manifests itself as a depletion capacitance. So now, because this node is not tied to VDD, this node moves. You're modulating this capacitor, and that means that you've got an extra capacitor effectively on the source node. And Saurabh shows it right here in this handout that he put together. There's always a bulk to ground capacitance, to the universal ground. And if you connect the source to bulk, you're effectively connecting that substrate capacitance to your source node. Whereas if the bulk is connected to a small signal ground, this substrate capacitance doesn't manifest itself. Okay? Yeah?
Would you also get a depletion capacitance then? If you tie your bulk to your ground, you tie bulk to whatever your source, whatever your substrate is tied to.
Bulk is your substrate.
Yeah, but you still get the same depletion capacitance from
Yeah, you do, but there's no signal going on it. Because now, and look, like the thing is that the capacitance goes from the bulk to the universal ground node. Can you see this? Is this picture big enough to see on the screens? If this node is, if the bulk is grounded rather than tied to source, that capacitance doesn't hang off your source node. Okay? And where might this come in particularly to sort of bite you? And this comes down to what I was talking about before. Common mode is a function of frequency. Common mode gain is a function of frequency. And let me see, am I covering everything I want to cover? So okay, so the standard diff pair, and this time I've drawn it with just resistive loads. Doesn't really matter what I put up here, okay? We know that, so if this is M1, this is M1, we know that ADM, can you guys keep down a little bit, equals GM1 times R, right? And we know that ACM is equal to GM1 times R over 1 plus 2 GM. I'm going to drop the 1 subscript. 2 times GM R0. Okay? You've solved this a number of times. Okay? Now, well, what if all of a sudden you have a big capacitance hanging off your source node? Okay? You've got this big capacitance. We can replace this R0 with an equivalent Z0, okay? And so what you end up getting is equal GMR over 1 plus 2 GM Z0. And Z0 is equal to R0 parallel 1 over J omega, let's call this C0. C0, which is equal to R0 over 1 plus J omega R0 C0. Okay? And now what you can see, first let's look at this qualitatively. At low frequency, this tail impedance is very, very high. This capacitor basically is an open, so you get the low frequency common mode gain. At very high frequency, however, this capacitance looks like a short to ground, right? And now the degeneration in the tail is basically zero. There's no degeneration. So at high frequency, you would expect this common mode gain to be equal to the differential mode gain. Because it's not only a virtual ground, it's actually a true AC ground in common mode stimulus as well. Does everyone understand that? So that's why you don't want to have too big of capacitance on this node. It'll kill your high frequency common mode gain. Or it won't kill it, it will increase it, which is a bad thing. Okay? And so you can actually do the small signal math, and you end up getting, so you plug this in, you end up getting ACM as a function of omega is equal to GMR over 1 plus 2G. Sorry, I keep forgetting to turn off my phone. R0. You get the low frequency. Times 1 plus J omega R0 C0 over 1 plus J omega R0 C0 over 1 plus 2 GM. Okay? So what you see is you have the low frequency component. You've got a 0 at 1 over R0 C0, and you've got a pole at a higher frequency. So actually when you plot this out, so the low frequency is, ACM0, which is GMR over 1 plus 2 GMR0. At 1 over R0 C0, you have a 0. So now at that frequency, the small signal gain, the common mode gain, starts increasing. And then at high frequency, at 1 plus 2 GM over R0 C0, it balances out. And actually, if you calculate what that value is, you get GMR, which is what you sort of expect it to be at high frequency. So as you can see, you have a big capacitor here. Yeah, tying your source to bulk will minimize the VT of this, so it'll increase the common mode range of your input devices. But it comes at a price. And whether or not that price is worth taking, whether or not it's worth using, is dependent on how the rest of your design is. So I'm not going to tell you whether to go one way or the other. I'll leave that to you to figure out. Okay. You're going to ask what the best method is?
More or less.
Yeah. Intuitively, it really depends on how, okay, so now let's talk trade-offs. How important is it? Well, what you need to figure out is how big this capacitance is, right? Because basically at high frequency, forget about up here, because if you're all the way up here, then your common mode gain is equal to your differential mode gain. Therefore, you failed spec categorically, right? So let's assume, if you can keep 1 over R0 C0, so you have your F3 dB. It depends on where your F3 dB is. If you can push this out beyond your F3 dB, then it doesn't matter that you have this extra capacitance, okay? But realistically, what will probably happen is that you'll maximize your F3 dB as much as possible, so you'll be somewhere in here. At that point, the common mode gain is basically, GM over 1 plus, well, GMR in this case, or whatever the R is, 1 plus 2 GM times 1 over J omega C. So the absolute value, you take the absolute value of that. And you just need to make sure that that's small enough. So I don't really know. I mean, because beyond this frequency, the degenerating impedance is that capacitor, right? So chances are that'll be small. So it's basically, you'll have, it'll basically be R load times omega C over 2, roughly. And you just need to calculate, well, will that meet spec when you cascade in everything else you've done? Chances are, if you have multiple diff pairs, then the gain, the differential versus common mode gain of each of those subsequent diff carriers will be high enough that you probably almost certainly could do this. But if you only have one diff to single stage, and then you have a bunch of either one or more single stages, you do the rest of the gain in just with single-ended in, single-ended out, then you may or may not be able to make it. I went over that. So the two areas, as I said before, the two areas to focus on are frequency response and good biasing. So good biasing might mean, depending on how you choose to implement your circuit, having bias currents that are totally independent of supply. That's one method, right? But if you do this totem pole thing, which might not be such a bad idea, you might actually need a portion of bias that's independent of supply and a portion of bias that's directly dependent on supply. And just one final note. So let's assume you create your bias structures. So bias 1 so I1 is equal to I fix 1. So basically, there is no, like I1 is totally independent of supply. So it's just a fixed current. And you also have a bias 2. Now let's say I2 is equal to K, some constant, times VDD. So it's totally proportional to supply. Well, you need something that's mixed, right? How do you do that? In this case, it's really easy. You just sum these two together in the right ratios, right? You have like M1 here and M2 here, so that you'd end up getting I out is equal to M1 times I fix plus M2 times K VDD. So by choosing these mixing parameters, you can get the exact mix of fixed and proportional bias that you want. Okay? Any other questions about the project? For those of you who want me to go over the totem pole stuff again, stick around. Otherwise, enjoy your weekend and good luck. And keep your eyes, over the next couple of days, keep your eyes peeled on the news group in case there are any other project-related announcements. Yes?
If our circuit passes the test bench, can we assume that it reflects enough one the way I'm from?
There are a couple people who have asked. There's some discussion on the news group. I haven't had the opportunity. Saurabh made the test benches. I haven't debugged them yet. If it passes the test bench, chances are that you didn't consume too much current. But if you know that you're consuming too much current and you pass the test bench anyways, then that means that our test bench is buggy and it's probably going to be fixed. So, yeah. Well, I mean, is it buggy? Or okay. Oh, so I need, for the time being, assume it's fixed. We're going to take a look at it today and make sure we've got everything working. You should. I mean, well. Except for the bias, independent bias. Well, if you don't, I mean, if devices go into triode region, then their gain's going to drop off.
I mean, for initially you want to bias the current that is dependent to the VDD. So you have to, it's like I wrote a kind of, yeah. So you have this kind of structure, like this, right? So I have to size this very big.
All these devices, in order for this to work, all these devices are in saturation.
This one actually cut off because this one is so big.
No, it's not in cutoff. If this is in cutoff, that means there's no current flowing.
No, there is current flow.
Then it's not in cutoff. The definition of cutoff is no current flow.
But the output from the spice say is cut off. the test branch dot list, test branch tree dot list.
Says it's in cutoff.
Yeah.
Well, I mean, you're basically
But there is
biasing this right on the edge, right? It's VGS equals VT. Because you want this voltage to be exactly VT, right?
Right. I actually I calculate how I get this value is I use VT divided by the
Yeah.
current I want.
Right. So this voltage is at VT. So that means this device has a VGS equal to VT. So VGS minus VT equals 0. So it is right on the edge.
Okay.
That's my point.
Okay.
So Spice might
okay?
say it's in cutoff. Yeah, it's fine. I mean, but realistically, it's in saturation.
Okay.
Okay.
And the spice output showing that these two current are identical.
Well, they should
Yeah, they
because
should.
of this, right?
Okay. So this one should be fine, right? We don't need to worry
Yeah,
about
it's
it.
fine.
Okay. Thank you.
I have a question. In the differential mode, this is not a virtual ground, right? It is
It's
only
not
true.
exactly a virtual ground. It's pretty close.
So do we have to take care of this node, the frequency at this node, for
Yeah.
differential mode?
I'm sorry, say that once more.
Do we have to care of the frequency of that node?
I mean, if this actually worked, sort of, but not really. I mean, it doesn't really have an. It has a predominant effect for common mode gain. It doesn't have a predominant effect for differential mode gain.
Okay, so
So basically, not really.
okay,
Okay.
okay. So we have to basically ignore this.
Well, you can ignore. You don't have to.
Okay, okay,
Okay.
okay.
Uh, so with this right here, back to the super source folder, I won't use it for the alpha stage. I want to know that this uses feedback, negative feedback.
Yep.
That means it creates a pole zero pair, right?
You know what? It's been a while since I've analyzed that circuit, so I don't recall, but I think so.
Okay, so how exactly do we, can you help me? I was trying to analyze myself, so how would I go about analyzing it?
Let's talk about it later. Okay.
Okay.
I would use zero value time constants for it,
Okay.
and then understand that there's a
When can we talk about it later?
when I'm like
Walking out?
in 15 minutes or so.
Okay.
I mean, there are a lot of other. That's a long discussion.
Okay.
So. Yes.
You said you should use a multiple stage differ.
You could. I didn't say you should. I said you could.
You could, yeah, you could for the every common mode. But how do you want to set those differs together, connect them together, to just to not to without a common mode, without a different working mode?
Oh well, you could do. I mean, if you had resistors.
He wants to get over to
Like you could just have. Right. You could do that. Another thing you can do. So. And basically, what you need to do is you need to have. So this is tough, right?
It's difficult to say.
That's difficult. Well, what you can do something that's actually really simple. It might not have the swing you need. You need some form of common mode feedback. I forget how this works. So this can be to a bias,
Yes, but from the supply independent.
right? And then you can have. There are lots of different ways to do it. You can have like basically. This. You can don't make this a constant current. So basically, if these common modes in differential mode, if this goes up and this goes down, the first order, like these go antisymmetric, so the current is constant. If these both go up, then it pulls more current, which pulls us back down. So this is a technique. And you have to basically look at simple method for common mode feedback. And common mode feedback is kind of outside the scope of this class.
But so you mean spare to use.
If you want to do this, then you have to start looking at some more advanced material.
And if I want to add for two stage for for the tail current to decrease the common mode.
Sure.
Then it will help me.
Help you low frequency, and you'll still.
But for the high frequency.
Well, Well, you tell me.
Doesn't matter. Just
It probably won't matter. I mean, yeah, unless that's some way to decrease, unless you're able to decrease the capacitance on that node. Okay. All right. So, are you guys here to ask questions, or did you want to see the totem pole stuff again? Okay. Let's do the totem pole stuff briefly. Oh my God, Scott. So, did you have a quick question about totem poles, or was it a long, involved?
What's the benefit?
Oh, sure.
Just kind of jumped into it.
The point of using this is that it enables you. It's basically a common source stage,
Yeah.
but the problem with common source stages is that, like, if you do this stage, and you know that this needs to source a certain amount of, like, some I load, it means that I bias has to be at least I load. You do this. This is an output stage where you can basically make the quiescent current of these devices. When I load is 0, these currents can be pretty darn small. But when you basically bring this up, like this voltage goes up, so this voltage goes down, this guy can source a lot more current. Let's say at this, well, these two voltages go up and down together. You understand that? So, if you need this voltage to go down, this voltage is going to go up, right? These voltages are going to go up. So that means this guy turns on hard and can source as much current as you need, which is what happens here. But when this in the other direction, there's no control over this current here.
Okay.
So you can't. When this goes down, this guy turns off, but this guy doesn't pull any more current. Whereas here, this guy turns off, and this guy starts sucking more current. So it's a way to get better efficiency.
Okay.
Okay?
But how can that help the 3dB frequency? It's something like
It doesn't necessarily. It doesn't help the 3dB frequency per se. What it does do is it frees up current for you to use elsewhere to increase the 3dB frequency.
Maximum over all the lines? Like, everything coming out of your VDD?
Wait, what?
Is that because of the maximum supply current? That's for your whole circuit?
Yes.
Everything coming out? So
Everything.
Not individual lines?
Yeah. Were you? Yeah.
All right.
Well, I mean, fine, individual lines, but one of the lines is the supply. It's the total current.
Okay.
It's not the maximum current per device.
Yeah, okay.
Because then you just put let's say you wanted, let's say you wanted this guy to source 5 milliamps with some W over L.
Go 5 of them.
Just 5 of them in parallel, each one is sourcing 1 milliamp. Yeah. And what you care about is the total power dissipation. Okay?
Actually, I have some question about this line. We use 2 differential plate and 2 buffer here in order to maintain this voltage at about like 0.8.
Okay.
This output is about 0. Yeah, it's roughly around 0.8.
Okay.
But then like it turns out we kill this 3dB already. I mean like we ship this 3dB here off the clock.
Right, because now you have low output impedance driving this, so the Miller isn't affected so much. Okay.
But the problem is like I have no idea. Even though like I put another, because I calculate the gain of this stage is about 200. The gain about this stage is about 7 to 10.
Okay.
And then the gain here is about 10.
Okay.
But the problem is like, so I think like the dominant pole will be around here. This is not equal, right? So dominant pole I think will be around here.
Yeah, it'll be the Miller cap here. Yes.
But then like I put another common gate here.
You cascoded it. Okay.
This now doesn't help the 3dB at all. I have no idea why that happened.
I think it's too nice to say no.
Oh yeah, I mean he was like, basically was like,
What it probably means is that that's not your dominant pole.
was that yes?
You've got enough other poles in there that you're limited. It should help you. I mean, the thing is, are you sure that this device is in saturation?
Yeah. Oh wait, this two, yeah, I'm sure. I tested that.
They're all in saturation.
Everything is in saturation.
Except for this one on showing
This
for
was
the.
on
Oh, yeah, right. That should help. I mean, have you done the analysis of your poles?
It's probably going to be really
yourself to see where the poles are and what frequencies they're at to match them up?
How you do that?
You did that in your homework. .pz.
Yeah, I just find out all the pole, but I just get a pole, but I don't know which point it is. Where the pole is.
Okay. Well, another.
I can just do some like calculation to figure it out, but
Well, there isn't a straightforward way to do it. I mean, you should see what your dominant pole. Do you have one? So get rid of this cascode device. Do a pole zero analysis. See if there's one dominant pole. Okay. Okay. And does that dominant pole come out numerically to be the pole that you see here, the Miller pole, or is it something else?
It's a little bit smaller than the pole I see here.
But it's on the same order. It's within like 20, 30%.
Yeah.
Then it's probably that. When you put this cascode in, did that Miller pole get any better?
Well, if there is any.
But not quite. Just about like 2 or 3
No, anyways.
megahertz.
From what to what?
He'll be like.
What was it originally?
From like before I put this in.
Working with me.
No, what were the two frequencies that you got?
The first one I got about like 6 or 14 something.
It went from 14 to 16?
Yeah, 16, 17 something.
I don't know. I mean, yeah, you kind of just have to hack through it.
Because before we put this in, we only get about like 4 mega.
Sure, because this load, because the load looking into a source follower is small, because this capacitance gets millered away, right?
But then I put this in, it goes up to like 17 14 mag.
Well, that's to be expected. So it could be your pole could be here. Have you? I mean, because you have a Miller cap here as well, right? So you should look at the Miller cap here. And maybe you got rid of this pole. It's conceivable that these two poles were about comparable. You got rid of this pole, and now this one is dominating.
So
Because
we try to size this one really big. Doesn't change the BDB frequency that much.
It's just right to test this pole here, so we size this like to about like
100 times larger.
Oh, because of this. Yeah, I don't know. You'll just have to. The only thing I can say is keep working on it. All right. Anyone else?
So can we walk or so?
Uh,
Stay here?
yeah, I'll stay here for 5 minutes. I should go.
So can you? All right. So we're planning on putting this in at our dominant pole area.
Okay.
I mean, yes.
So
We already have low resistance, so we don't really know how to. So it's not the resistance problem. We just need to cancel out that pole.
So you've got basically like the driving circuit is essentially something like this.
No. What for what?
What's driving this?
Oh, a diff amp.
And what is this driving? It's
another
driving.
diff amp.
So
No, that's the output, isn't it? It's the output stage.
This output stage? No.
No. What is this driving?
You feeding it to a diff amp?
Yeah, feeding into another diff amp.
A diff amp.
Why are you doing
what's the other diff?
Like, so it'll be a single-ended. I mean, I'm gonna put 2 of these. Basically, these 2.
So what you're doing is you're doing this, and then 2 of these guys,
Yeah.
and then another diff amp.
Yeah. Because the pole is right here. The pole is right here. The dominant pole is right there. Like, crap. You really don't.
You don't even need. I mean,
I can't get rid of
why
that
do you need a
pole.
super source follower as opposed to just a standard source
I heard it gets rid of your dominant pole.
You heard? Who'd you hear it from?
The book. like you read the book and then it says, oh, it uses negative feedback to follow how this cancels. Like, oh. And then I was remember negative feedback uses a pole or a 0 combination to cancel out.
I mean, so the thing is, so this is driving. So what you're saying is that this is driving a high gain transistor, where Miller effect matters.
Yes.
Okay, and it's driving high gain. Okay, so if it's driving high gain, then basically what you want to do. And so let's look back and call this RS, and call this.
Was it only RS that's the problem? Is it only low impedance that helps this? It can't be. But the impedance is 1 over GM.
Right, so I mean, have you looked at, what I was going to say is, have you looked at just using a source follower instead of a super source follower?
Well, I don't need that then because I have a 1 over GM anyway resistance. Like my pole is at like 900 megahertz, but I need to get higher.
Not so I don't know. Your first pole is at 900 megahertz.
No.
No.
No. No.
What do you say?
No.
I think you're doing okay. I mean,
No,
like I
no,
haven't.
no, no.
Why
Okay,
not?
it's not good.
I think you're doing.
No, so I'm just asking for help. It's not
I
good
don't.
enough.
I don't. It's not good enough.
Yeah, it really is not.
So have you designed your? Have you run any test benches on your amplifier?
I'm just pretty sure ours doesn't work.
Okay. I think 900 mega. I don't
No,
know.
no,
I
no.
don't know how fast you
I've
should be
I've
able to get
known
it.
I've heard gigs.
Really?
Multiple
What
gigs.
guy? Well,
Huh?
the guy who goes to stare, Jack.
You know,
Okay.
He got up to 8 gigs with his roommate. It was 8 gigs.
The same guy who's.
I agree with
He's not. Wait. His roommate isn't doing it for him, is he?
I know.
Probably not.
Yeah. Um.
You guys should just give us a target range. Like you get this F1.
No,
20
no, no, no.
points.
We're not gonna do that for you.
No, no,
'cause
I
then-
don't want that. Okay, forget. So how does this work? It has to cancel out the pole. I don't see
It doesn't cancel out the pole. The point here is that it can't like the
Why
books
would
that
people use it in the first place?
because it provides a very low impedance.
Lower than a regular source power?
Exactly.
Oh, it does.
Yes. It's
Because
like
of the negative feedback?
yes.
It lowers the impedance? Okay.
Yes.
Alright, how do you do that?
What?
Yeah,
Wait,
how
what's
does it?
what's the output impedance?
All right. Well, I haven't
It's not
done this.
just 1 over GM. Man.
It's not 1 over GM.
Yeah, I already have 1 over GM as the output, so I don't want that.
Yeah. So
that's why
I
I
actually
did.
haven't done this in a while,
Mhm.
and I should just tell you to do it yourself.
No, that's the problem. I was working on it long.
What's that?
I was working on, and I don't guess I don't know too much about feedback yet because we just touched on it.
Sure. Well, I mean, you can still analyze it. Okay. Okay. So we're testing. I'm just going to use our standard techniques.
Okay.
So we're testing the output impedance.
Yes.
Pain in the ass.
Yeah, sorry.
I think you're going to end up getting 1 over GM squared RO, but I just want to figure out how you get that. It'll take me a little while, so I don't have time for that. But you can do it yourself.
You actually, can you tell me how you did it then?
How the hell? Yeah,
Because I remember the I remember the answer. I mean, basically, what I would do here is I would plug in the small signal model
Okay.
to solve it. There are
Are you sure it will work with the small signal model?
small signal model always works.
Always works.
Small signal model is
Always works.
the God's honest truth.
Okay. Let's
So,
just work on it then. Let's
let
just
me-
do it.
Okay.
Yeah, it's not so bad. I want to see how do you do this in feedback.
So you're looking to do it in feedback?
Yeah, feedback. So this is a. So this is IN,
This would not
IFB.
be an output stage, though.
Huh?
This would not be an output stage. This is not an output stage. What would you use at the output then?
Use the inverter.
Okay.
Use everything you put up in class.
Okay. So what's the loop gain? So,
AF.
well, you can calculate the loop gain yourself by breaking the loop. You have to recognize where the feedback point is. And so this is current in, current out, which is why it's hard to analyze feedback.
Shunt. I don't know.
Yeah, I never keep track of that either. So, okay, we know, if you look at the loop gain, we know that Vx is equal to Yeah, it's a common gate. So
So
you get
GMR.
well, but it's current drive input.
Okay. Okay. So it just should be the current. It buffers the current, so the current coming out of here is the same current going in.
Exactly. But the current
I-
can't go. The current has to go
Through the resistor.
through the resistor.
Okay.
Right.
I see.
And there's also this GM shunting it.
Mhm.
So yeah, basically like you can get the analysis here, and you'll end up getting that IFB is equal to GM R0 IN. Okay, so this is the loop gain.
Loop gain. Uh-huh.
And then when you close the loop, you'll end up getting a Z out or Z in, depending on if you call it. It's called a Z out. Is equal to the standard input impedance, which is 1 over GM, over 1 plus the loop gain, 1 over GM R out, which is roughly equal to 1 over GM squared R out.
How is that smaller than 1 over GM? Because your RO is huge. I don't know how-
Because it's, oh wait, I'm sorry. Because 1 over GM times GMRO is much smaller than 1 over GM.
Oh, sorry.
Yeah. I thought I made a mistake for a second. All right, now I need to go. But you can keep this.
Oh, yeah. 1 over R. It's not R, it's 1 over R. Okay.
I have a quick question. Where does zero come in from?
Let's go.
Is there a way to introduce a zero to cancel a pole?
It's not easy.
So just you gotta shift the pole instead.
Yeah.
There's something in the book that says they could pole splitting, force a pole to the left and to the right.
That's more for stability.
Stability. So
Yeah. So stability, so what happens is that now you've got all these poles. So if you're to actually look at
super gain.
wait, what?
No, your gain gets. How's the gain for to stay with the R is so low? Gain's killed, right? The gain's killed.
No,
Or
it's
pretty low.
still a buffer. It's a voltage buffer with a low output impedance.
Oh.
Like concurrent, like if you're saying so, the GM of this equivalent. If you're calculating gain as GM times R
What
out,
the big GM is for this?
big GM is bigger,
Oh, I see.
and you can calculate that yourself as well.
Makes sense.
So yeah, that's like so. If you have, let's say you have a lot of poles, what's going to end up happening is that like let's say all the poles are at the same frequency, you're going to incur a lot of phase shift before your gain drops down very low. So if you feed that back, it turns negative feedback into positive feedback. So actually what you want to do is, and positive feedback will cause instability and your circuit will oscillate. What you want to do is you want to figure out a way to make one pole be dominant and push all the others out to high frequency in order for the circuit to be stable. We're not doing closed loop feedback.
like 3 dB even
Low.
smaller.
Yes.
I see.
Bummer. Well, see, but what ends up happening is that it'll move your 3 dB frequency lower. But what ends up happening is that feedback pushes your 3 dB frequency back up.
Oh really?
Yeah.
How would you propose
Why?
beyond the scope of what we're doing now, right?
You're not using feedback here. So Professor Broderson will sort of show you.
Okay.
Okay.
I gotta find another way to see if I can move my 3 dB.
Yeah, this is an open loop design. So you basically just want to push all your poles high constants to low values, push your poles high.